Hello everyone, and welcome to this discussion of significant figures. Now, first of all, we need to discuss what is a significant figure. What's the purpose of it? So, let's do this by example. Suppose we're measuring the length of an object with a meter stick. Now, this is a little weird of a meter stick, right? This meter stick only has 10 little demarcations in it, which means each one is about 10 centimeters. So, if we look at this, we count them up, 10, 20, 30, 40, 50, 60, 70 centimeters. Would you say that it would be accurate to say it's 70 centimeters long? Well, of course not. It's clearly more than 70 centimeters long. Well, then how about saying it's 80 centimeters long? Again, that seems ridiculous because it's much less than 80. So instead what we might want to do is say, well, it looks to be about a little less than halfway in between, so maybe 74 centimeters long. In other words, notice what we did here. We took an estimate. And not only did we estimate, what we did is we took our smallest calibrations and in our heads kind of broke it up into 10 pieces and estimated how many of those tenths there were. And this is a general rule that we're always going to use with our measuring devices in here. Always estimate to the nearest tenth of the smallest calibration. Now, sometimes that'll be more important than others. If we're actually using a meter stick like we used in our circle lab that has millimeters on it, well, tenths of a millimeter are really, really small. That's not going to throw in much error. But let's say you're using some sort of graduated cylinder in chemistry class that has big separations between the markings. We might want to estimate to the nearest tenth of the smallest calibration there in order to be able to have a more precise measurement. Because even if you were wrong here, even if you said it was 73 or 75 instead of 74, that's still closer than 70 or 80. Remember, 74 centimeters is 0.74 meters. There's 100 centimeters in a meter. 100 centi is 100. So 0.74 meters should be able to convert back and forth, hopefully. Now, what if we had a meter stick that had 100 calibrations? In other words, the smallest calibration was centimeters. Well, just as we mentioned before, we could very simply estimate to the nearest tenth now of a centimeter. But look at this one. It is clearly right on top of this hash mark. This is 10, 20, 30, 40, 50, 60, 70, 1, 2, 3, 4. So it's exactly on the 74. It's not off to either side. So do we leave it at 74? Well, no, not if we want to use the device to its full precision. Then we have to estimate one more place. But how many tenths are there in between? Well, there's 0 tenths in between. So since the smallest calibration is centimeters, we can estimate to the tenth of a centimeter, or thousandth of a meter, or millimeter if you want to say it that way. So notice here, this 0 is important. Right? It's not like in math class where you can just throw that 0 away, or like your calculator that would never write the point 0. Because when we look at this measurement, we can realize, hey, look, we estimated to the nearest tenth of a centimeter. If we just make that 0 disappear, now it looks like we only estimated to the nearest centimeter. And if we're paying for a device that we can use to estimate to the tenth of a centimeter, we want that in our measurements. Remember, this would be 0.740 meters. Right? This 0 would mean 0 thousandths of a meter, or 0 millimeters exactly. Now we know here the 0 is the estimated digit because we made the measurement. And if we were going to make every measurement ourselves, we wouldn't need the rules that we're going to talk about shortly about significant figures. Okay, we need these rules because we need to understand if we share a measurement or if we look at somebody else's measurement, what precision are they really talking about? Does this 0 count or not? So these are the rules of significant figures. So we're going to define here significant figures as exactly what we did here. All the digits in a measurement that are marked calibrations plus one estimated digit. The one furthest out to the right is always the estimated digit. And the estimated digit is always tenths of the smallest calibration. We'll do some examples here in a moment to see how that works. So here are some rules for counting significant figures. Okay? I'm not going to ask you to cite these rules on a test. I will ask you to cite these rules on a worksheet, however, so it might be good for you to get these down or to look at the reading that I gave you on significant figures on which they appear. So the first rule is kind of obvious. If it's a non-zero digit, it counts. You would never just add a 4 onto the end of a number. 4s are never placeholders. So if you have a 4 at the end of your number, it means that that was the estimated digit. Now, here's one that's a little more interesting. The next 4 rules are all about zeros. What if your zeros are bounded by non-zero digits? Well, then the rule says they count. For example, 402 meters. Well, let's look at this measurement. Okay? The 2, because of rule 1, counts. This means we estimated this to the nearest meter. Maybe we used a piece of string that was 10 meters long, right? So we could estimate to the nearest meter. Well, if we know, or we can estimate, to the nearest meter, then we have to know how many tenths of a meter there are. Right? So if it's bounded, it counts. So there are 3 sig figs in this measurement. All 3 digits count. And this is precise to the nearest 1 meter. Next rule. Oh, and by the way, it doesn't matter how many zeros are in between. If you have a non-zero to the right and a non-zero to the left, all the zeros count. If the decimal point is expressed, so this is where we get into whether or not there's a decimal point in your number. It's not trivial like it is in math class. If there's a decimal point expressed, all zeros following non-zero digits are significant. Remember that we read numbers from right to left, so following means to the left of a non-zero digit count. So 42.0 meters. Well, obviously the 4 and the 2 count because they're not zeros. So does this 0 count? Well, according to this rule, there is a decimal point, and this 0 follows the last non-zero digit. So it counts. So there are 3 sig figs in this measurement, and this measurement is precise to the nearest tenth of a meter. So maybe we were using a piece of string that was 1 meter long, so we could estimate to the nearest tenth of the meter. How about 42.00 meters? How many sig figs? Well, the 4 and the 2 count because they're not zeros, rule 1. And it says all zeros following the non-zero digit are significant if there's a decimal point, and there's definitely a decimal point. So this is 4 significant figures. In other words, we estimated to the nearest hundredth of a meter. This is precise to the nearest hundredth, so both these zeros count. Again, notice how different this is than math class, where you just write this as 42. But in here, putting these zeros on make it a more precise measurement. And if you're using precise instruments, you want to keep the precise measurements. How about 420.000 meters? Well, hopefully you see that that would be 6 significant figures. Again, the 4 and the 2 aren't zeros, and it says all zeros following the non-zero digit. It doesn't matter where the 0 is, if the 0 is before or after the decimal point. If there's a decimal point, zeros following non-zero digits count. So all 4 of these zeros count, and this is precise to the nearest, tenth, hundredth, thousandth of a meter. We estimated to the nearest thousandth of a meter, or millimeter, if you will. Next rule. What if there's not a decimal point? Then zeros following the last non-zero digit are not significant. They're placeholders. So for example, you might get a number like 420 meters. No decimal point. So this 0 is just there because if you didn't put it there, it would look like 42. You need to put it there as a placeholder. So that's only 2 sig figs. This is estimated to the nearest 10 meters. It's only precise to the nearest 10 meters. Maybe we were using a piece of string that was 100 meters long. So we estimated there were 2 tens, or 20. But we couldn't estimate to the nearest 1. How about 4,200 meters? Well, again, there's no decimal point, so zeros following, and it doesn't just say 1 0. All zeros following are not significant. So these 2 don't count, they're placeholders, and this again is only 2 sig figs. This is precise to the nearest 100 meters. These 2 are just placeholders. By the way, I tend not to use commas. You'll see that in my bigger numbers, and the reason I don't is because in some countries they use a comma as a decimal point, and so that gets very confusing for foreign exchange students, for example. Right, so they might write this number up here with a comma and think it was 420.000 meters. And so I tend to leave a space in between my groupings of 3, and a decimal point is a decimal point. How about 4,200 decimal point meters? Well, the 4 and the 2 count because they're not zeros, but now we have a decimal point, so these 2 zeros count. So this is 4 sig figs. This is precise to the nearest meter. We estimated to the nearest meter. So here we have an estimate to the nearest 100 meters. Here we have an estimate to the nearest meters. How would we write this if we wanted to estimate to the nearest 10 meters? If we only wanted 3 sig figs here? If we wanted the first 0 to count but not the second one? Well, you can't really do that just with decimal points. But there is another way to write really big and really small numbers that will help you sometimes with significant figures. And that, of course, is scientific notation. So say we wanted to write 4,200 with 3 sig figs. We would write it as 4.20 times 10 to the third meters. Because when you write scientific notation, you only look at the first number, the number out in front, if you will. You don't look at the 10 to the third, doesn't count in the number of sig figs. That's talking about placeholders. So this is 3 sig figs, 4.20. So here we have the same number written 3 ways. And again, the reason why in science we want to write it that way is it speaks about the precision of the measurement. Where did we estimate to? Here we estimated to the nearest 100 meters. Here we estimated to the nearest meter. Here we only estimated to the nearest 10 meters. This is a more precise measurement. Again, if you're using a more precise device, you want to use the more precise measurement. Now, we're going to practice this on a worksheet tomorrow, so don't freak out. Once you use the rules a little bit, it's not too hard to count. And it's really the zeros that throw them out, or that throw them off, sorry. Last rule. Zeros preceding means to the right of, because we read from right to left. The first non-zero digit are not significant. They are placeholders. 0.042 meters. Well, this is precise to the nearest tenth, hundredth, thousandth of a meter. The 4 and the 2 count because they're not zeros, rule 1. But these are preceding. Right? They're out in front. So yes, there's a decimal point, but look at the difference between this and this. These are after the non-zero digit. These are before the non-zero digit. Notice it doesn't matter where the decimal point is. It matters where the non-zero digits are. So these don't count. They're placeholders, and that's 2. We could write this, by the way, as 4.2 times 10 to the negative second meters. Write it in scientific notation. And that would clearly tell us there's only 2 sig figs. Right? But sometimes we don't use scientific notation. How about 0.0420 meters? Hopefully you're saying, hey, there's 3 sig figs. Well, obviously the 4 and the 2 count. So of these 3 zeros, which one counts? That's right, the one following the non-zero digit, since there's a decimal point. These are preceding, rule 5, they don't count. So let's do a couple of examples here. I want to know 2 things. And this will help us do operations with significant figures in the next day or so. How many sig figs are in each measurement, and what's the precision of each measurement? Or another way of saying this, what did we estimate to here? So 56.1, they're all not zeros, so they all have 3 significant figures. And I'm going to cite the rules here. You can go back and look at them, or they're in your reading, right, because they're not zeros. And this is precise, since this one counts, to the nearest tenth of a meter. So let's do a couple of quick examples. Remember, this is a video. You can stop it, rewind it, look at it again. 44.10 seconds. Well, the 4, and the 1 count. Does the 0 count? Hopefully you said it does because of rule 3. There's a decimal point, and it's after, to the right of, the non-zero digit. So there are 4 sig figs, and this 0 is the estimated digit. So this has a precision of tenths, hundredths of a second. Precise to the nearest hundredth of a second, or we estimated to the nearest hundredth of a second. So maybe our stopwatch only recorded to the nearest tenth, and then we estimated to the nearest hundredth. 300 decimal point grams. Well, the 3 definitely counts. Do the zeros? Yes. Why? Rule 3. There's a decimal point, and they are after the non-zero digit. Again, it doesn't matter where the decimal point is. It matters where the zeros are. They are after the non-zero digit, so they count when there's a decimal point. So that means this 0 is part of the measurement. It's the estimated, so we estimated to the nearest 1 gram or nearest gram. That's the precision of this measurement. Precision is kind of how many decimal places, right? It's what we're estimating to. 3.0 times 10 to the negative second meters. Well, first of all, remember that in significant figures, you only look at the number out in front. So, in other words, look at this as 3.0. That has 2 sig figs. The 0 counts because it's after the non-zero digit and there's a decimal point. Only the coefficient out in front counts. Now, to get precision, it's really hard to do that with scientific notation. So let's write this out in standard notation. 10 to the negative second means we move the decimal point 2 places to the left. So we get 0.030. And by the way, this 0 counts. These two don't. They're before the decimal point. Or sorry, before the non-zero digit. This one counts. If you take this one off, you've changed it to only 1 sig fig. So this is our estimated digit, which means it's precise to the tenths, hundredths, thousandths of a meter. One more example here, I think. So, how many sig figs? Hopefully you're saying 3. Well, that's great, but which set of zeros count? The ones before the non-zero digit or the ones after, given that there's a decimal point? Well, Rule 3 says only the ones after the non-zero digit count. Rule 5 says the ones before don't. Now, if we write this in scientific notation, this is 2.00, these two zeros need to count, times 10 to the negative second centimeters. So it's a little clearer to see that there's 3 sig figs there. What is this precise to? Well, this 0 at the end counts. So this is tenths, hundredths, thousandths, 10,000ths of a centimeter. That's a pretty precise meter stick you're using there. Probably a caliper or something like that. Or maybe a laser sight that you can use to measure things. All right, one more example, I guess. 302.040 kilograms. How many sig figs? Well, this 0 is bounded. If we know how many 1s there are, we have to know how many 10s there are. This 0 is bounded. If we know that there were 4 hundredths, we have to know that there's 0 tenths. This 0 is after the non-zero digit and there's a decimal point, so it also counts. So the 3, the 2, and the 4 count because they're not zeros. These first two zeros count because they're bounded. This 0 counts because it's after the non-zero digit and there's a decimal point. Rules 1, 2, and 3. Since this 0 counts, this is precise to the nearest tenth, hundredth, thousandth of a kilogram. That's, by the way, gram, if you will, if you want to convert. Oh, there's one more example. 40,020 meters. Now, key, no decimal point. These two zeros are bounded. If we knew how many 10,000ths of a meter there were, and we knew how many tens of a meter there were, we had to know that there were 0, hundreds, and thousands. So these two both count. This 0, however, is after a non-zero digit, and there's no decimal point. That's a rule 4. So there's only 4 significant figures. So this 0 doesn't count, which means this 2 is our estimated digit, and it's in the tens place. So it's precise to the nearest 10 meters. Or you could write it this way, 4.002 times 10 to the 4th. Notice we don't use that last 0 because it doesn't count. It's not a significant figure. So again, significant figures, first brush at them here, are a way for us to communicate with one another. If we're not doing the measurements ourselves, it's often hard to tell with zeros whether they were something you measured, there were just 0 hundreds of meters here, or whether they're just placeholders. So the rules of significant figures allow us to communicate with one another. It's a language thing. And then we can tell where our precision is, where we estimated in any measurement.